As unmanned aerial vehicles, UAVs, continue to evolve, engineers are shrinking them down to astonishing sizes, entering a realm where machines begin to mimic nature itself. The push for smaller, more agile, and more stealthy drones has inspired a new class of aircraft: micro-air vehicles, MAVs. These machines are so tiny they can slip through windows, fly down hallways, and even navigate inside ventilation systems, just like insects. The ultimate goal: to create machines that are invisible to radar, impossible to hear, and capable of surveillance so precise and discreet they can observe a room without ever being noticed. Achieving this requires radical rethinking, not just in size, but in aerodynamics, propulsion, and control. At the cutting edge of this effort is the AeroVironment Company in California. Here, engineers are developing MAVs for both military and civilian applications. One of their most impressive achievements is a flying disc just 6 inches in diameter. Though it resembles a toy, it's a marvel of miniature engineering. This tiny disc is equipped with an onboard video camera, a live transmission system, and a GPS receiver. It's so small and light, just a few grams in total, that it's completely invisible to radar. With a battery-powered motor, it can fly up to 6 miles, relay live images, and return safely to base, all without ever being detected by conventional sensors. But miniaturization brings unique challenges. Components like the flight computer, receiver, and propulsion motor must be smaller than a coin. At this scale, even breathing too hard near the workbench can destroy hours of progress. Engineers work under microscopes, and losing parts is an everyday risk. "We've lost more components to sneezes than to crash landings," jokes one technician. Despite the difficulties, the team is pushing boundaries. They're also working on miniature helicopters, but as blades and rotors shrink, they become less and less efficient. The problem is fundamental. Air doesn't behave the same at miniature scales. To a MAV, air molecules are giant obstacles. The process of flight becomes more like swimming through water than gliding through sky. To solve these problems, researchers are turning to nature, specifically to insects, which have mastered small-scale flight over millions of years of evolution. Insects like fruit flies, dragonflies, and hawk moths achieve extraordinary lift and maneuverability using flapping wing motion, something engineers are now racing to replicate. Already, experimental MAVs with flapping wings have been built. These mimic the way insects beat their wings in figure-8 motions to generate lift. But matching the efficiency of a real insect remains an elusive goal. Most mechanical wings fall far short, using more power and delivering less lift. To understand what makes insect flight so powerful, scientists have gone deep, both literally and figuratively. At Cambridge University, Dr. Charles Ellington has spent over 25 years unraveling the mystery of insect aerodynamics. Using high-speed video and mechanical replicas, his team has built large-scale models of insect wings that replicate their complex motion. Insect wings don't simply flap up and down. They also twist, bend, and change shape during every beat. Many species use a figure-8 motion combined with changes in angle of attack and wing curvature to maximize lift. The most complex models must simulate this movement from wingtip to wing base, across both leading and trailing edges, all within milliseconds. The team even developed a giant robotic moth wing that flaps at a slowed-down pace, once every 2 seconds, to observe the intricate movement more clearly. In reality, a moth flaps at 20 beats per second. Controlling this requires an advanced computer system capable of synchronizing 4 different types of wing motion in real time. But understanding the motion wasn't enough. Dr. Ellington's team needed to understand the aerodynamic effect too. So, they turned to wind tunnel smoke visualization, a stunning method where smoke is blown across a flapping wing to reveal airflow patterns. What they saw astonished them. As the wing moves downward, the sharp leading edge slices through the air, generating a leading-edge vortex, a swirling tornado-like low-pressure zone that clings to the wing surface. This vortex sucks the wing upwards, creating 2 to 3 times more lift than conventional fixed-wing designs. This insight explains how tiny insects achieve such powerful flight, and it has revolutionized MAV design. By replicating vortex-based lift generation, engineers are getting closer to true insect-inspired flight. Soon, researchers believe, MAVs the size of a dragonfly will be able to fly autonomously through buildings, air ducts, and even underground bunkers. Equipped with miniature cameras, heat sensors, and data transmitters, these cyborg insects will become the ultimate scouts, stealthy, agile, and intelligent. But they'll also be durable. Without pilots, these craft can be optimized for stealth and resilience. Their flight endurance can be extended with new lightweight battery technologies and energy harvesting systems, making them ideal for long-duration surveillance missions. This new generation of MAVs won't just be a marvel of engineering. They'll be masters of disguise. Covered in lightweight synthetic materials that reflect minimal radar and emit no noise, they will be nearly impossible to detect or destroy. Their only real threat? A well-placed fly swatter. And this is just the beginning. Within the next 3 to 5 years, experts anticipate the rollout of fully autonomous insect-scale drones, capable of urban reconnaissance, search and rescue, environmental monitoring, and even covert intelligence work. The battlefield, the city, even the home could soon be watched over not by satellites or helicopters, but by dragonfly-sized MAVs floating silently in the air. In this miniaturized frontier of flight, nature remains our greatest teacher. The future of aerospace engineering may well lie in replicating what evolution perfected millions of years ago. As we continue in the next segment, we'll explore how this innovation in small-scale flight is inspiring larger radical aircraft with no wings at all. Machines that hover, twist, and fly without ever leaving a heat signature behind. Welcome to the age of gyroscopically balanced saucers, laser-guided liftoff, and wingless aviation. Stay with us as Infinity Beyond continues to chart the future of flight.